Chapter 34 should actually be easy for us because we've already done a lab that did images. So first step is just images from plane mirrors. So imagine we have a mirror here. And so you are right here, there's your eye, and you're looking at an object. Okay, so you have an object maybe right here in front of the mirror. And so you know that light from one end of the object is going to hit and reflect. This angle equals that angle. So, but you look at it and you look off in that direction to see it. Okay. And if you had another eye, so you got two eyes, and this eye is also looking at the tip of the object, that light looks like it's going there. Well, since this angle equals that angle, then that equals this angle. Okay, and since this angle equals that angle, then it's also equal to that angle, which means that this line and that line are exactly the same as this line and that line. So that means it's as if the object is right over here. And so what happens is that this distance right here, the distance of the image, has to equal the distance of the object. If you just do a little bit of geometry there, similar triangles. Likewise, if that is equal to this, okay, then that means this height equals that height. So the height of the image equals the height of the object. And so with that, we have that for a plane mirror, the image is behind the mirror. Obviously, the real object right here, your eyes are right here looking at it. You got two eyes looking at it. Your depth perception comes from both eyes looking, seeing at a slightly different angle. It's called parallax. And so the object looks like it's behind the mirror. I mean, if you were to actually have a friend go around and look behind the mirror, obviously it's not there. There's no image there. And so, but it looks like it. So we call that a virtual image. So, because it's not really there, it just, your eyes see light as if it's coming from something that's there. And so this virtual image behind the mirror, it's the same height as the original object, and the distance behind the mirror is the same as the distance the object is in front of the mirror. So here we have for a plane mirror. Okay, so now what we're going to do is we're going to look at a curved mirror. Now, to make the math easier, we are going to imagine a spherical mirror. Okay, now the way a spherical mirror works is, imagine a sphere. We have the center of curvature of the sphere, which is right there. Center of curvature, your book calls C. Okay, and then what we're going to do is we're going to kind of cut the mirror in half. So, or not just half, but just part of the mirror. So a portion of the mirror right here. Okay, now draw a line right through the center of curvature. Imagine we have an object over here. Light going to the center of the curvature hits the mirror, goes straight back out. Okay. Light going like that comes in an angle like that. So that means the light from this point up here at the top of the object comes together at a spot right there. Well, it turns out it's even more interesting than that, because it turns out that for a spherical mirror, center of curvature here, if light comes in parallel, it tends to bounce so that angle incidence, or angle reflection all come together at a spot that's halfway to the center of curvature. We call that the focal length. So that's 1/2 of the curvature. So if you imagine the focal length is half of the curvature, light coming into the focal length hits the mirror, goes straight back out that way. Well, that's interesting, because that would mean that all this light is coming together at one spot. So likewise, in a lower spot of the object comes together here. So what happens is, if you were to put like a piece of cardboard right there, then all this light hitting the mirror would bounce back and be imaged on the cardboard. And so you would have an image it'd be a real image because you could put something there, all the lights congregating right there, so you call that a real image. A virtual image, the light's not really coming together. With a real image, it really is coming together. And so now what we want to do is investigate that real image right there. Okay, and so let's neaten up my drawing here. So here is center of curvature, focal distance is right there. So let's have an object that's out here somewhere. Okay, so light coming in straight this way is going to go right back through the center of curvature. Okay, light going through the focal length comes straight back this way. Light going to the center hits and goes right back where it came from. And so you can see that here is going to be the image. So this is my object, HO. This is HI right here. So the height of the image. Now notice that the image is upside down for a virtual image. So what we want to do is we would be interested in figuring out, well, just how big is that image? And so what you do is you can look at it and say, well, I know that if I draw a line like this and like that, because a light beam going straight from the peak of one peak of the object to the center line here, same angle. Well, this right here is your image distance. That right there is your object distance. If this angle equals that angle, then we have similar triangles. So HO over DO equals HI over DI. Well, sort of. We should put a minus sign in there. Minus sign because the image height is negative, it's upside down. And so we would then say that minus HI over HO equals, well, that's interesting enough, DI over DO. So the spacing here makes a difference. Now, HI over HO, or negative HI over HO, this is our magnification right here. So if we want to talk about magnification, or rather magnification is HI over HO. Well, since it's negative, this is negative magnification. Okay, negative magnification does not mean it got smaller. Negative magnification means it's upside down. So a negative magnification of 0.5, a magnification of minus 0.5 means it's upside down and half the size. A magnification of minus 1.25 means it's 25% larger and upside down. A positive magnification simply means it's right side up. Okay, so we call that an erect image. So now we have this relationship here that gives us this relationship that we just did here, and now we can look at that and say, well, this is going to be a measure of this, and we look at, wait, we can go one step further. Okay, we can also say, okay, that look at this right there. Okay, those angles right here, those angles are the same. So that means that again we can say that HO. Okay, so let me erase this down here. So we can say that HO is to this distance. Well, what is that distance? That's going to be DO minus C. That's going to equal HI over C minus DI. Okay. Well, let's do algebra there. So we divide through here. HI over HO is going to be equal to C minus DI divided by DO minus C. Okay. di over do is going to be c minus di over do minus c. Right, actually, there should be a negative hi up here, because that was upside, it should be a negative number. So, and we got this because minus hi over ho is the same as di over do. Okay, so now we cross multiply. do minus c over do equals c minus di over di. Okay. So again, 1 minus c over do equals c over di minus 1. Okay, do some algebra. 2 equals c over di plus c over do. 2 over c is 1 over di plus 1 over do. Well, c over 2 is the focal length. So we could then say 1 over f equals 1 over di plus 1 over do. This is our basic equation for spherical mirrors and where you find images for mirrors. So that's our basic mirror equation. 1 over f equals 1 over di plus 1 over do, our basic mirror equation. We're going to later find out that it doesn't have to be just mirrors. You could have a lens. Okay, the lens has a focal length, so light coming in here focuses through that focal length. The lens works both ways, so light going that way focuses through that focal length. So if I had an object over here, there's a focal length there, light going through there goes off straight, light going through the middle keeps going, light going straight goes through the focal length, and so you get an image right there. Well, it turns out that if you take whatever this is, fold it back over to that side, make a mirror image, it looks exactly like with the mirror. So that means that the equation for images with lenses, 1 over f equals 1 over di plus 1 over do. The exact same equation. And so this equation is the crux behind almost all of chapter 34.